In this video, we're going to learn how to multiply radical expressions with different indexes. In this example, we need to multiply the fourth root of q to the third times the fifth root of q to the fourth. And we notice that we have different indexes. Here we have a fourth root, and here we have a fifth root. Unfortunately, we can't multiply radicals with different indexes. So how do we fix this? The first thing that we need to do is convert each of these radical expressions into exponential form. In other words, convert the fourth root of q cubed into q to the 3/4 power. And now let's do the same thing for the fifth root of q to the fourth. The fifth root of q to the fourth in exponential form is q to the 4/5. Now, at this point, hopefully we realize that we can use our laws of exponents to simplify this expression. When we multiply like bases, we keep the base the same and we add our exponents. So we'll have q to the 3/4 plus 4/5 power. But to add these exponents, we have to have a common denominator. Well, the common denominator between 4 and 5 is 20. And 3/4 is the same thing as 15/20. And 4/5 is the same thing as 16/20. And 15 plus 16 gives us 31/20. So our final answer is q to the 31/20. But because we started out by multiplying radicals, we now need to change our final answer back into radical form. Q raised to the 31/20th power is the same thing as the 20th root of q to the 31st power. So now let's dive a little bit deeper into this process to see if we can see behind the scenes exactly what was going on here. The first thing that we need to notice is that when we transformed this expression into exponential form, the denominators of our exponents were the indexes of our original expressions. And that totally makes sense. That's what we would expect. We talked about that in previous videos when we talked about how to rewrite radical expressions in exponential form using rational exponents. So that's not a big deal. That's what we expected to see. But here's the connection that I want us to make. Because each of these indexes were the denominators of our exponents, when we were finding a common denominator so that we could add these exponents together, we were really finding a common index. So finding a common denominator for exponents is the same thing as finding a common index. So now, without going through all of the steps that we just did here, let's rewrite each one of these radicals with a common index. Well, we know that our common index is now going to be 20. So I'm going to have the 20th root of q to the something power times the 20th root of q to the something power again. But the question is, when I change this fourth root to a 20th root, how does that affect the exponent of 3 on the inside? Well, the exponent of 3 is the numerator of my exponent when I write this expression in exponential form. So the same question would be, how was the numerator of my exponent affected when I went from a denominator of 4 to a denominator of 20? Well, to transform the expression from a denominator of 4 to a denominator of 20, I had to multiply the denominator by 5, which means I also had to multiply the numerator by 5. So our 3 transformed into a 15 because 3/4 is the same thing as 15/20. Well, the same thing applies. To transform this 4 into an index of 20, I had to multiply by 5. So that means I have to multiply the exponent of 3 by 5 to get 15. So what does this mean for us? This means that when we're working with radicals, that we can treat the index of the radical and any exponents in the radicand of the radical just like they are fractions. As long as I multiply the index and any exponent in the radicand by the same number, I can build up my radicals the same way I build up fractions. In this case, I had to multiply the 4 by 5 to get an index of 20, which means I have to multiply the 3 by 5 to get an index of 15. So the fourth root of q cubed is the same thing as the 20th root of q to the 15th. Now let's carry out that same process for this expression. I know that I need to turn this index of 5 into an index of 20. I have to multiply 5 by 4 to get 20. So that means I have to multiply this 4 by 4 as well to get 16. So the fifth root of q to the fourth is the same thing as the 20th root of q to the 16th. And look, now we have the same indexes. We have a 20th root times a 20th root. And now we can just multiply outside to outside and inside to inside. 1 times 1 on the outside gives us 1. And then because we're multiplying a 20th root by a 20th root, the result's going to be a 20th root. And then when we multiply inside to inside, well, that's q to the 15th times q to the 16th. Well, I'm multiplying like bases, so I keep my base and add my exponents. So I get my final answer again as the 20th root of q to the 31st. Let's look at this example. Here we need to multiply the 8th root of 9 by the square root of 3. Again, I notice that my indexes do not match. I have an index of 8 multiplied by an index of 2. Well, if I want to be able to multiply these two expressions together, they have to have the same index. What's the common denominator between 8 and 2? Yeah, it's 8. So let's rewrite the square root of 3 as an 8th root of something. Now, the 8th root of 9 we won't have to change because it already has the index that we want it to have. So what do we need to multiply the index of 2 by to make it an index of 8? We need to multiply it by 4. So if we multiply our index of 2 by 4, we get an 8th root. But if we multiply the index by 4, we also have to multiply the exponent on the inside by 4. Well, the exponent on the inside is a 1 because we have 3 to the first power. But when we multiply that 1 by 4, we get 3 to the fourth. So the square root of 3 and the 8th root of 3 to the fourth, they're the same thing. And now we have matching indexes. Now we can multiply. That gives us the 8th root of 9 times 3 to the fourth. 9 times 3 to the fourth is going to be a pretty big number that I'm going to have to try to manipulate so that I can make sure that it's fully simplified and find an 8th root hidden in that number, and that might become a little cumbersome. So I'm going to help myself out here, and this is a trick you need to put in your back pocket. Anytime we're working with radicals, and we can rewrite one expression using the same base as another one, we want to do that. Here's what I mean. I'm going to rewrite this 8th root of 9 times 3 to the fourth as the 8th root of 3 squared. Why? Because 9 is 3 squared. And that's still times 3 to the fourth. Now notice I have like bases underneath the radical sign. So because we have like bases, we can use our laws of exponents again and say that's the same thing as the 8th root of, keep the base and add my exponents. It's the 8th root of 3 to the 6th. Well, that's the same thing as 3 raised to the 6/8 power. Well, if we see a fraction like 6/8, we're going to reduce that, right? So let's reduce 6/8 to 3/4 because 6/8 and 3/4 are the same thing. So now we have 3 raised to the 3/4 power, and if we convert that back into radical form, that's the 4th root of 3 cubed. And of course, 3 cubed is 27. And the 4th root of 27 is the same thing as the 8th root of 3 to the 6th. This is the simplified form, whereas this is not. So what did this exercise show us? not only can we multiply an index and an exponent underneath a radical symbol by the same number, but we can also divide them by the same number. Notice that to simplify this expression, we divided the exponent inside by 2, and we divided the index by 2. And we ended up with the fourth root of 3 to the third. And we just simplified 3 to the third as 27. So not only can we multiply an index and an interior exponent by the same number, to simplify radicals, we can also divide the index and an interior exponent by the same number. All right, one last example. Let's multiply the square root of a times the fourth root of b. Again, I notice that I have different indexes. I need them to be the same. What's the least common denominator between 2 and 4? Well, obviously that's 4. So we want to rewrite the square root of a as a fourth root of something. Now we won't have to change the fourth root of b because it already has the index that we want it to have. But we do need to manipulate the square root of a so that it has an index of 4. So what number do we multiply the index of 2 by to get an index of 4? Well, obviously we'd have to multiply it by 2. But that also means that we have to multiply the interior exponent, which is a 1, by 2 as well. 1 times 2 is 2. So that means the square root of a is the same thing as the fourth root of a squared. So now we have the fourth root of a squared times the fourth root of b. We have the same indexes, so multiply outside to outside and inside to inside. Doing that gives us the fourth root of a squared b.